Professor S.K. Singh is the CSIR CBRI Delhi Center's Chief Scientist and Scientist in Charge, as well as ACSIR's Professor. His research is focused on novel cementitious materials, alternative aggregates, solid weight utilization, carbon sequestrations, geopolymers, and structural distress detection and rehabilitation. He has made substantial contribution to the subject by sponsoring over 125 research initiatives, publishing more than 120 papers, and holding a patent. He has won various accolades, including the Outstanding Concrete Technologist Award from ICI in 2023. In this session, he will discuss sustainable alternative binders, challenges, and opportunities. I welcome you, sir.
Uh, Thank you very much to all. As suggested by that B2B, I'm thankful to B2B Purchase Magazine who has asked me to deliver a lecture on sustainable alternative binders, challenges and opportunity. At CSIR Central Building Research Institute, Roorkee, we are working on several years on different type of materials, which involve from composite cement to pozzolanic materials as well as LC3 and other tertiary and binary system of the composites. But recently, for last 15 years, we are working on geopolymer concrete, and recently for last 3 years, we are working on alkali activated binders, particularly which will be in a dry form, just to add water things. Let's coming to this one. That cement is a really most used material, and we have recently celebrated a 200 years of innovations or invention of cement. And if you look into that, chemistry of cement has not yet changed. Still, we are working in the same line, same products, modifying some that it's microstructural and other things. So huge quantity of cement is being produced, and we are going ahead with more than we are being by 2050 to 6 billion tons. And we are presently have a capacity of 650 million tons and been producing about 350 million tons of cementitious binder, and huge amount of greenhouse gas is being emitting, particularly by calcination of limestone on ordinary Portland cement. And if you look into the same time, another building constructions material, that is steel, right now in India is producing about 143 million tons and targeted to 300 million tons by 2030. And both these materials are producing huge amount of CO2. If you look into the cement, it has been producing about zero point 0.8 to 0.85 ton of carbon dioxide into the atmosphere for per ton of cement productions. Particularly, that I am talking here as a cement productions means ordinary Portland cement. And if you look into the steel, which is being same way producing about 2.5 tons per tons of steel production. So both are producing huge quantity of waste material as well. So it is the right time, and we have to come with the right technology to substitute cementitious binder with different type of binders. It may be composite or supplementary cementitious material, or we should come into that eco-friendly cement-free binder using industrial byproduct and having a pozzolanic properties. So by this way, we can reduce, in a great amount of anthropogenic effect of CO2 emissions. So, that if you look into overall problems which we are being addressing, and as we have said, 5 ton of cement productions consumes about 5 gigajoule of energy, huge quantity of 1.5 tons of raw material for per ton of cement productions, and it's account about 7% of global CO2 emissions. And that varies by the company. 1 kg of OC releases about 0.75 to 0.85 kg of carbon dioxide. This is the recent data, and that day by day we are increasing. Not only this, Also, we are being discharging SOx and NOx in huge amount. So we have to look into that next system. So as scientific and other producers, they are working how we can reduce the clinker factor. So continuously utilizing industrial byproduct, maybe it is a fly ash or ground granulated blast furnace slags or silica fume or calcined clay or any other materials is being used, and every efforts are being made to reduce the clinker factor less than 50%. Also, you know that we are continuously working for other type of binders, which is being alkali activated binds, which is being no cement, only utilizing some chemical and industrial waste, and that is being known as geopolymer, which is being a very low carbon sustainable binder to reduce carbon footprint. And not only that, it is being sustainable, also we are utilizing what we have been producing huge quantity of industrial byproducts. I have tried to list on different type of binders. Different groups are working all over the country. It may be calcium aluminate cement, calcium sulfoaluminate cement, composite cement. We have a code also on composite cement, composite limestone cements, alkali activated binders. Where recently we are working, my team is working on this, and super sulfated also we are working on carbon negative cement and LC3. But if you look into that, every binders that coming up having some issue or some drawbacks or some challenges. But if you want allowed to be used into the constructions field, then development cannot become up, no innovations can become up. So we have to definitely utilize those newer low carbon binders, looking into if some minor effect or some things are there which is not affecting much on our durability and strength property, definitely will go. So but quickly, who is not understanding the geopolymeric reactions, so let's we are taking a fly ash which is rich in silica content, alumina and sodium oxide, which is by nature is not hydraulic. We are adding alkali activators such as sodium hydroxide and sodium silicate, which is making richer sodium as well as a silica oxide by this activator. So giving some temperature, we are converting or we are producing NAS, that is a sodium aluminum silicate. But because that temperature is a issue, so if you are don't we want to develop these properties on ambient or what is been a normal temperature, so we have to add some material which can quickly react with the this aluminosilicate glass available into the precursor like fly ash, GGBFS, or other things, so which can generate exothermic reactions and generate heat, and later on we can convert into the geopolymeric binders. So by adding that GGBFS into the fly ash and adding alkali activator, so available calcium oxide will quickly react with the available materials activators, and it will generate huge energy, and by this internal temperature will increase, and by this fly ash and other material will get activated and convert into the NAS. So this is the basic chemistry about the geopolymer. I'm not going, we have made different products, building products, that paving blocks, cellular concrete roads in our, so in 2015 we made a road in our CBRI campus, if you can see here, without having any cement. Then in Dadri, all are being sponsored by the NTPC in other part of the country. Not only that, we have made a geopolymer self-compacting concrete and also building products like beams, slabs, and other things. Also in a buildings, we have made a building also with this geopolymer. But that one major issue, that there is a sodium hydroxide. Handling of those corrosive material is a big challenge, and by this way we are not able to promote in a bigger way in a different part of the world or country, but that we are making, but scalability is a big issue. So looking into that, we started working on single part alkali activated binds, we can say, which is, that in a dry form and just add water, we can say, and developing. And we are looking it, we should be work like similar ordinary Portland cement or type of cement. And we are working in that directions, and different precursor material has been processed. Sometimes it's required calcinations. We are carrying out the calcinations and adding those activators. Maybe that sodium metasilicate pentahydrides are different type of that activators we have tried and optimizing that one and developing this thing. So what is been driving force for this one part alkali activated binders, that if you look into that, we have huge quantity of raw materials and fly ash slag, and rather than we have a legacy fly ash in some part of that, definitely slag is being utilized a majority by the cement industry, and we can use that one to developing this. Not only this, it is going to reduce the carbon footprint by utilizing into the binders. Also, government is required to be, that use of what that different uh, our that guidelines has been promoted, and by this way we can go ahead with this and further to support this type of binders, by adoptions like they have a fine on legacy as, and that fly as should be utilized into that within the 300 kilometers, some gadget notification, etc. Also, that we have to utilize locally available products, so that we can have a cost effective raw materials. And continuously we have been collaborating with the different research organizations. So by this overall, that we can develop this material. So that here this is only aluminum silicate based our available precursor, and alkaline reagent, different type of reagent we can use and make it. Here we tried that how this overall alkali activated binders works. So this is been given in my paper, how it is been ion exchange is been participating, then hydrolysis, then breakdown of the glass network, release of silica and alumina, then polymerization, then regeneration, gelation, and specific essence. And by this way overall binder is being developed. So overall here I have tried to give you overall approach and methodology, how we are developing this single component. And recently we have a transfer of technology adding some microfibers into this for repair of sewer line and other things which is been corroded very extensively. And this development of alkali activated binder ready to use, that why I am writing geopolymer, basically what we are developing, that is alkali activated binder, but people are little bit aware about geopolymer, so we are writing because there is we are using huge amount of ggbfs which has been rich in calcium oxide. So it is been basically we are activating the this calcium oxides by this, and not only promoting a circular economy, also we are conserving our natural resources. And polymerizations by alkaline solid activators as well as aluminosilicate precursor materials. So different studies has been carried out and it has been published by different papers. However, that there are challenges and barriers in this alkali activated just add water system, because that there Alkali activators are in liquid form, which been immediately react with the precursor or aluminosilicate and give. But here, slow reaction polymerization process. Also, that materials, what raw material, fly ash, GGBFS, or any other material has been variability, because that amorphous quantity has been, sometimes we are getting very less. So it's a challenge of that reactions. Also, very limited data is available upon different type of solid activators, because whatever solid activators we have to use, you should have better performance. And also very less studies has been carried out on optimizations and different other behavior, and lack of proportioning and guidelines. Definitely there is no code for this single component, because it is being this one quickly, that item is being in a dry form, where in two part it is being in liquid form. And mainly dissolutions effect, both give exothermic reactions, and by this we have somewhat quick reactions into two part, where somewhat slow reactions into one part. And that in this case reaction start after adding the water, where that this liquid alkaline solutions pre-mixed with precursor and start its reactions. In one part, definitely we have a huge opportunity to be scalable. We can go ahead with that, because we are used to been using this cement, ordinary Portland or PPC cement, for several years, and just adding water and mixing. So this will give better prospects. And also, that overall cost will be lesser in one part geopolymer binder as compared to that two-part geopolymer. Here we have carried out a different, fly ash, GGBFS, and optimized. I'm not going into the details, but definitely it is going to have that if you are looking into the silica, if there is fly ash is 52.11%, not necessarily our silica particles are going to participate into the reaction. So amorphousness study is must through ritual or any other methods, to establish how much reactivity is available with this. So these are the some studies. This is what same and other of the our products strength properties, that this is we tried with the give it that life cycle cost analysis of OPC binder. And this is a two-part geopolymer binder and single component geopolymer binder. So by this way, and different mortar mix we have tried, and given here being studies. Also, it is only cost of productions. This is nothing with the any profit or any other cost. So if you are making M45 grade mortar per cubic meter, cost will for with the OPC will come 5270, where two part geopolymer it will come 5768, where one part it will be about 4,500 or so. So it has been cost effective. Also has been done on durability, and other mechanical properties has been studied. So that but different activities, particularly on alternative binders working, we have carried out a very extensive research on activating steel slag, which is by nature it's a crystalline, and particularly LD slag and LF slags into the laboratory. We have done a trial, and successfully, that we have tried with the 30% of LD select activations and developing the binders of the same. Also, we tried with the making a clinker as a other, because they have a similar, alumina, silica, and other materials, so it can be utilized. So, and we are promoting that one by the different alternative binders. Recently, we have worked on low grade limestone into the cementitious binder, because good quality limestone is also a big challenge. So thank you for listening. That I tried it.